So we're going to look at polymer chemistry today. Polymer chemistry, in terms of the types of reactions that we're going to look at, are no different from what you've been exposed to. So it's nothing really new in terms of reaction types. It's just defining what type of molecule constitutes a polymer and what doesn't. So a monomer has certain functional groups, or has the functionality or the ability of joining to other things. If you look at my choo-choo train, a choo-choo train has 3 cars, but it can be elongated. We've all been at that stop sign where you're waiting at least like sometimes 10 minutes waiting for this long train to pass through with a bunch of cars on there. So the idea is one single repeating unit is known as a monomer, but the catch is that this monomer must have like 2 sort of, plugs so that it can plug onto the next one and allow for the continuation of this chain. So one single entity is known as a monomer. A monomer always has some sort of functionality present that allows it to elongate and add or continue to bond with more monomers. 2 of them together is a dimer, 3 of them is a trimer, but usually after monomer and dimer, it's mostly jump to polymer. Many of the mers join together. Okay, when we're naming polymers, so how do I name a polymer? First of all, if it's a repeating unit, you write the word poly for many, and then you simply attach the name monomer, the monomer name to it. Okay, and that's how we name it. So that's the nomenclature, easy peasy. There's 2 types of monomers, branched and straight chain polymers, and then you've got addition and condensation polymers. So branched polymers have branches on them. Okay, and because they've got branches on them, it's harder for them to get nice and close. And why would they want to get nice and close? Well, LDFs, right? Intermolecular forces would be at play. If I had a straight chain polymer, then the fit is better, right? I'm doing a squiggly line because technically it's zigzag if it's like, say, a hydrocarbon. And so the fit is better, which means more surface area contact where the London dispersion forces can interact, right? And so you'll get a nice compact, whereas with the branch one is loosey-goosey. There are polymers that will actually link covalently to other polymers. And so these ones are different in strength because now they're locked in space sort of thing, right? Through covalent bonds. The other thing we're going to look at is we're going to look at addition and condensation polymers. So these, the second categories, it defines again, the functional groups and the type of reaction that is preferred in order to make the polymer. So addition reaction takes a different route to make the repeating polymer chain, and condensation polymer take a different route. We talked about condensation reactions yesterday. So in your mind, condensation means removing of water. So you could possibly consider what, factors or functional groups must be present for you to condense something, okay? So polymers are everywhere. They're in nature, they're in industry, right? We wear clothes that are polymers. Plastic that we use is a polymer. Teflon that we cook on is a polymer. Styrofoam, polymer. The type of polymer that you make and its properties depend on, again, the identity of the monomer, okay? How long it is. So think about LDFs in length, right? How long is the polymer chain? And the shape of the polymer chain that's made thereafter, right? Is it straight chain? Is it branch? Does it have like groups hanging off that don't allow for close attraction? Those sort of things. So straight chain polymers obviously will pack well together. I already talked about that. And because they pack together, they're stronger. That makes sense. So, when you are recycling, and most people are really good about it, you'll see on the bottom of plastic containers almost like a triangular sign. It wasn't bad. It started out good, then I messed it up. But they'll do like HDPE in there. And there's even like a number. So low density polymer versus high density. Low density means it doesn't pack well, right? So it's made up of a branched polymer. High density means it packs really well. And so likely it's made up of a straight chain polymer. So by controlling these factors, you can make different properties. Like the outcome of the polymer can be sort of controlled. Okay. So polymerization is basically the process in which we're linking monomers together in a repeating sequence. Okay, so polyethylene bags. So you may have noticed your parents or even your grandparents don't call it like a plastic bag. We'll just go, "Oh, give me a plastic bag." They'll say, "Get me a polyethylene bag." And the first time you may have heard it, you're probably like, "What the heck is she talking about, or he talking about?" So what you need to know is that the common name for ethene is ethylene, right? The IUPAC name is ethene. So when I have a bunch of ethenes hooked up together in a long sequence, it makes me my plastic bag. You know, those plastic bags that are now found everywhere, like you'll see them. It makes me sad that there's so much plastic in the world and such less uh, control that there are trees in the summertime. You guys take a look, even now, because there are no leaves yet. If you guys take a look, there are certain trees that have plastic bags all around the branches, and it looks like a plastic tree. So there's something that needs to be done in terms of our consumption of plastic. More so, your group needs to figure out ways of recycling it better. So I was reading something where they said that um, in spite of us at the local level, at the personal level, doing our part, sometimes when it gets to the recycling plant, it gets thrown away still. So it kind of makes you worried about what's going to happen. We're already facing climate change crisis already. People didn't believe in it. Now it's really coming to the forefront. You can see um, changes in weather and the dynamics and the number of hurricanes and whatnot. That there's something not right. And part of it is the first of all, the energy expended to make these items like plastic bags, but secondly, the amount of pollution that they end up causing, which then enters, food chains and us. So the greatest risk right now is to your health because you're so young, and then your kids. And the worst thing a parent can do is watch their kid be sick. So there's something that you guys need to be more vocal about at the political level, but at the personal level, if you go into sciences, this is it. This is where you guys need to really see if we can make a change and reverse what we've been doing. So polyethylene bags made up of ethene. The question is, how is it that ethene will hook up? So I can have a big pot of ethene sitting there, and nothing will happen. So we need some sort of push, right? I need some sort of initiation event that allows it to go. Well, in an addition polymerization, it's the presence of a peroxide bond. So something like hydrogen peroxide would be perfect. And all you need is some sort of um, precursor that cuts this open. When this opens up, what happens is you go through a chain, like a free radical mechanism, and I'm going to show you how that goes. If you remember when we did the mechanism to show addition reactions and I was proving Markovnikov to you, I used a double-headed arrow, a double-headed curly arrow to show two electron transfer. When we did kinetics and I did the free radical mechanism, I did a single-headed arrow. because that means one electron transfer. So what ends up happening is the two electrons that are held together get broken, and I end up making two RO radicals. You guys know that radicals are extremely reactive, extremely fast, and the reason for that is because you have a lone electron. It needs pairs. So it will now just, go insane trying to react with other entities to remove this radical as soon as possible. So if you have a large amount of ethene available, this radical will go ahead and react with an ethene. Okay, we know that ethene consists of a sigma bond and a pi bond, and the pi bond together with the sigma bond make an electron-rich center. The thing is, a pi bond, the negative is more dispersed top and bottom, right? P orbital. And so those electrons are more available. So what I'm going to do is I'm going to take the pi bond and I'm going to represent it by two electrons because that's what it is. So what happens now? This radical is dying to become stable, right? It wants to get rid of this single thing. So what it does is it goes ahead, breaks up the pi bond, and takes one of the electrons. So what did I do? I took the electron here, I combined it with the electron here, and now I end up making a bond. So I've got my hydrogens, the two hydrogens from before, and now I've hooked up an O and an R. I've still got my sigma bond. I still have my two hydrogens. Never leave what was there before behind. And now I've created another radical. So I had an initiation step, then propagating, right? And so now this one can go ahead and react with another, and I'll do the RO over here. Remember, this free spin, so it doesn't matter where you put it. But I end up now having another radical. So this is the radical that we made, right? I just put the electron in the front. This can go ahead now and combine with another ethene. And this will continue on and on until two radicals meet and stop the madness. So this electron will go with one of these electrons and make a bond, which means it's going to hook up to this carbon here. And then here is the second electron going into the carbon on the right side. I'm just going to move this over and up so I have more room. So what do I get? Well, I've got the RO, right? Use your eyeball, left to right, and bring everything back for the ride, okay? So I had two hydrogens here. I used to have a dot here, but that now linked up to this carbon, okay? So I'm going to make that bond. That carbon was there. It's got two hydrogens. It now has one bond, two hydrogens, and a radical. And well, guess what? Now that can continue. So this madness continues because you have excess quantities of ethene available up until the time when two radicals happen to bump into each other, and then the madness stops. So it could be this radical and this radical combining together to make a 1, 2, 3, 4, 5, 6 carbon chain, right? So in the terminating step, the last step is to combine any two radicals, and now you've got an even longer chain. And that's what's happening here. So the takeaway is that when you have addition polymerization, you're looking for the presence of a double bond. That double bond undergoes the free radical substitution mechanism, and it adds on to the ethene. And because there's a greater availability, I can't move it over, it's driving me crazy. Because there's a greater availability of ethene, it will, make for more chains with lots and lots of ethene getting added. I don't know why it won't let me manipulate this. I'll come back. Let's see if it lets me go back. It's so crazy. It gets caught up in its nonsense and it won't let me scroll there. So ethene then undergoes addition polymerization, where it is the free radical that dictates what happens. Okay? Now, will I make you write out this mechanism on the test? Absolutely not. Do I expect you to know that it's going to elongate and produce a certain long chain? Yes. So by the end of it all, when this is done, you're going to have R, O, and then you're going to have a bunch of CH repeats, right? That can go on and on depending on when the chain ends. So what we do is we kind of make square brackets around the repeating monomer, which was ethene, carbon and carbon, and we do N for however long it is. Okay? Now, the cool thing about additional polymerization is that if we replace the hydrogen with fluorine, you end up getting Teflon, that non-stick stuff on those pans. Okay? If you replace the one of the hydrogens, right, the ethene, if I replace it and I add a benzene, I end up making styrofoam. When I replace the hydrogens on one end with two chlorines, I get saran wrap. If I replace one end with a methyl and an acetyl group, I get plexiglass. So it's very cool how the functional groups present around the ethene end up producing very different polymers with very different uses, right? So it says draw a polymer for Teflon. So first start by looking at what Teflon looks like. Teflon is made up of ethene with 4 fluorines. When you get a chance, you guys should watch the video on having the Teflon flu. If you use non-stick around your house for cooking, around your house, yeah, that's what you'll do with it, in the kitchen, check that out. When I was taking industrial chemistry in university, our professor, this is like years and years ago, had mentioned studies where they had heated Teflon to high temperatures. And when I'm talking high temperatures, I'm talking about like turning it up on like medium to high heat on your stove. But even like testing it at slightly higher temperatures, they found that when birds were flying over these heated bodies, they would drop dead. So there are toxic things that are generated. Your non-stick pans are to be heated only to a specific temperature. Beyond that, you start creating these crazy things. So they found like toddlers sometimes start getting sick, especially if you're cooking in a small space and it's not ventilated. You might get health problems. So check it out. It's good to know how to use something properly, right? It's great that it's non-stick, but you want to make sure you're safe. So in terms of what is happening, what's going to happen is this guy is going to go and link over here, right? And then this pi bond is going to go and it's going to link over here. Something's going to start it, obviously, right? And it's going to start by linking here, and then the chain elongation continues. So if I were to draw a trimer of Teflon, 1, 2, 3, 4, 5, 6, it would have a CF2 repeat. Right over here, it's CH2 repeats. But in terms of identifying the monomer is made up of 2 carbons, right? And 4 hydrogens. That's your monomer. All right, so easy peasy, nothing crazy. So you're going to look at it and you're going to construct me my polymer. Okay, so the second category that we're going to look at is we're going to look at condensation polymerization. So condensation polymerization is different from addition polymerization. Addition polymerization requires the presence of double bonds. I couldn't find the monomer for this, but I understand there's a double bond here before it gets made into a polymer. So Condensation polymerization does not involve the same mechanism, first of all, or pathway to make it. And the identity of the monomer is different. What does condensation mean? Condensation means removing water. Well, if you guys remember, we did condensation reactions yesterday. And the idea was that, for example, if I had two alcohols hooked together, right, you could take water out, right, and link these two together. But if I want a polymer, I need to be able to continue, right, linking a long chain. So what I need now is I need a monomer that has functional groups on both sides. Because if it has functional groups on both sides, then I can continue the process of removing water endlessly as long as I've got enough monomers present, right? So my glob in the middle, so long as it's got two ends where I can remove water, then I'm good to go. So if you guys remember, the condensation reactions that we looked at was combining an alcohol, with an alcohol, and we made ether and water, right? Or we took an alcohol and we combined it with a carboxylic acid, and I made an ester. And if I took an amine and I combined it with a carboxylic acid, I made an amide. So the idea is for you to have condensation polymerization, you want to have functional groups with alcohols, amines, or carboxylic acids because they have those polar bonds that allow for the removal of water. Okay, so a couple of takeaways. When you have condensation polymerization, you have to have a monomer that has the correct functional groups, right? So any combination of alcohol, right, carboxylic acids, or amines will do, right? The second catch is that it must have two functional groups. So it should be difunctional, right? Two. If I don't have two on the terminal ends, I can't have that propagation property of linking one to the next, to the next, to the next, right? It just stops. So that is the biggest difference between addition and condensation is the presence of the functional groups change the chemistry in how it is made. So we're going to look at two polymers today, condensation polymers. First, we're going to make polyester, the stuff that we wear, and that undergoes condensation polymerization. The idea for making a polyester is that you're basically starting with a glob that has a carboxylic acid on both ends. So it's a dioic acid, right? Plus, it needs to have an alcohol, right, to take out water. But that also has to be difunctional. It has to have it on both sides because I want it to go on forever and ever and ever. So the idea is that when they're together, we can remove a water molecule, and now I've hooked these two together. I could continue this, couldn't I? And I could now add another acid on this side, and I can keep this going. So the question is, do the functional groups on either side have to be identical? The answer is no. You can have identical, you can have non-identical, so long as they fit this criteria. So long as they're one of these, then I can remove water because that's the most important takeaway there. So when we're making a polymer called polyester, the stuff that we wear, and polyesters have come a long way. They used to be very sort of rough and itchy. I remember back in the day when I was a kid, I used to hate them. They used to make me very itchy because I already have sensitive skin. And so I think it just added to it. But now, like they're selling clothing and you look at the tag and it's made up of polyester and it feels like that kind of distressed cotton. that's like super soft on your skin. You know the cotton where you had that t-shirt from when you were in like grade 3 and you refused to let it go? Yeah, yeah, we all do it. And we don't let it go because it's gotten so soft over time, right? That sort of feel they've kind of refined in polyester. So the hate for polyester that I had before, it kind of changed because I'm like, oh, this is kind of nice. So they've done more research and they've changed probably something about the functional groups that allow you to um, make it like more, it makes it more wearable. Okay, I'm going to squeeze in, I'm sorry, I drew it too big on the other end, another carboxylic acid. I'm going to redraw it. I'm going to redraw everything so I can squeeze it in properly. But what I'm trying to do is I'm trying to make a trimer. Okay, I'll just make it smaller. My benzene got too big. So C double bond O, OH. And then here's my benzene. I'll draw it much smaller. Okay. Here's my ethane diol. You've seen this before. We named it. Right? So it's 2 carbons long. And then I'm going to react this with another terephthalic acid. That's what this is called. Benzenes with 2 carboxylic acid groups on the ends. Okay, so let's take out water. So I can do this, right? And over here, I can also do that, right? And now I can draw the resultant trimer that I've made. And when I'm drawing the resultant trimer, you're going to start eyeball left to right, just like we did yesterday. Whatever's there must come along for the ride. So now I'm at C double bond O. Wait a minute, there's a line. I took out water. Where does it end up going? It goes to the oxygen there. And then CH2, CH2, line. Wait a minute, nothing happening. Oxygen there. CHO. Let me just put a line in there so you guys can see. Like that. And of course, we took out 2 waters, right? So what you will notice is it's called a polyester because we're making multiple ester bonds, poly, many ester bonds. So for us in our trimer, here's my first ester linkage, and here's my second ester linkage. Biology people must be happy today because the stuff they could do in their sleep now. Okay? So this is basically the setup for making a polyester. The second one we're going to look at that is condensation polymer is making an amide. Polyamides are called nylons. Nylons are tights. Most girls have had the pleasure of wearing tights. Those also itch me, luckily. And so polyamides are also based on a specific type of monomer that is difunctional again, and it generates a long continuous chain. Let me just show you. So take a look at a polyamide. A polyamide, again, removes water to create amide. Okay, so I've got, again, a difunctional carboxylic acid monomer, so 2 carboxylic acids at either end, and I have a diamine, 2 amino groups at either end. And what do? I'm going to take 1 hydrogen off, I'm going to put it over here, and now we can take water, right? And I end up making my amide linkage right here, and I make water. Now, if I got a bunch of the dicarboxylic acid and a bunch of the diamine, I'm going to make a nice long chain, right? So the nylons, the old school ones, are made up of adipic acid and hexamethyl methylene diamine, okay? Or really, it's made up of um, 1,6 or hexa 1,6 diamine, okay? Or 1,6 diaminohexane, same deal. But here we go. Let's draw what this would look like. So we're going to make a trimer again. So they both have 6 carbons total. So 1, 2, 3, 4, 5, and 6. And then we put the OH. So it's called a 6,6 nylon because it describes the number of carbons around it. The amine also has 6 carbons. 1, 2, 3, 4, 5, and 6. And then you put the other amine at the other end. We're going to react this again with another acid. And the acid one has 4 CH2 repeats in the middle, right? And then the 2 carboxylic acids to make 6. 6,6 nylon. So I've drawn my 3 monomers in a row. I'm going to go ahead and I'm going to remove water. And then I'm going to join it all together. So start at the left-hand side and bring everything along for the ride because they didn't participate, but they are part of that molecule, so you gotta make sure you're accurately bringing everything back. 1, 2, 3, 4, 5, 6. So 6 carbons. And then when I come to the carbonyl end, I stop and I realize I've taken the OH and the H out. So where does it link up? It links up to the nitrogen. And then you continue by bringing everything in that monomer. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, and 6. And then I slow down again. I have a nitrogen with a hydrogen. Wait a minute, there's a line there, and it hooks up to the carbon. So bring the carbon to the CO, and then you put in the rest of the molecule, of course, plus H2O. So in terms of the repeating theme here, it's creating this amide linkage. Question?
Shouldn't there be 2 waters?
Yes, thank you. There are 2 waters. Let's balance that equation. Good job. Okay, so polyamide, meaning having a monomer with 2 functional groups, which in this case have to be 2 carboxylic acids, and then the second monomer must have 2 amino groups to make the amide linkage. All right, and so we'll watch a video at the end, and I'll show you how this can be made. We are no longer allowed to make this in schools because they've taken away the stuff that's hazardous. So another example of a condensation polymerization, we talked about nature having polymers, is making proteins or a polypeptide chain. So amino acids are difunctional in that they have 2 functional groups. So here's one and the other. And they're not identical, but who cares? Because when you hook them up, they can still make amide linkages. So different amino acids have different, like instead of a hydrogen here, it's got different R groups, which then changes the outcome of the type of chain that you make and its properties. But the idea is still the same. You have an amine and a carboxylic acid. So the amine carboxylic acid come together from 2 different monomers. and you remove water, there it is, and you end up making an amide, which is known as a peptide bond. Okay, so if you have three amino acids hooking together, you're going to make a tri-amino acid chain, and it's held together by peptide bonds. And I believe they'll call like a multiple thing polypeptides. Okay, but notice how the functional groups are different, and that's totally cool as well. Sugars also undergo polymerization. When you're making starch from simple sugars, that act is making polymerization. Now, I wanted to show you in real life, sugars actually have this shape, not the nice cyclo structure that we kind of envision in our mind. They take this chair conformer shape. And the reason why they take this shape is to reduce like bond angle strain. So bond angle strain is the idea that all carbons want to have 109.5 when they're sp3 hybridized. But when they're in a cyclical form, they have to conform to the cyclostructure's bond angle. So think about cyclopropane, right? Cyclopropane has 60-degree bond angle. Meanwhile, these guys are sp3. And so they're aiming to be bigger, right? And so they're under a lot of strain. So in order to offset strain in um, larger ring structures, they start making these conformers. So this is known as a chair configuration. But what happens is this can flip up. And so all of a sudden you end up making a boat conformation. And then this can flip down. But going through those flip-floppy stuff actually ends up making it more stable. And repulsions are minimized and whatnot. But anyway, going back to polymerization, when I have two alcohols, I can make an ether, and that's what's happening here. So you're removing water, and you're making an ether linkage, which is now known as a glycosidic bond. So in biology, they have fancy terms to describe how it bonds, but it really is a condensation reaction, right? And the cool thing about this is because it's got alcohol groups on both sides, this can go on forever, right? So long as I have more sugar monomers present. Okay. Any questions on polymerization? Any questions aujourd'hui on polymerization? All right. So I have this worksheet, and it focuses more on condensation and hydrolysis reaction. So I'll do a couple of examples with you, and then we're going to move on to synthesis reactions. Let me just erase. Oh, good. It's already, eraser's already on. Oh, jolly. Okay. So take a look at the first one. It says identify the type of organic reaction represented by each of the following equations and name the compound. Well, I can name this 1, 2, 3. Propanoic acid. Unos, dos, two. So ethanol. This somehow reacts to make an ester. Remember, it's carbonyl, and you run away from the oxygen. So we definitely have a propanoate, and it's hooked up to an ethyl. The type of reaction, well, it looks like I made an ester, which means a carboxylic acid and an alcohol combined to remove water, and that's my proof for it. So this is a condensation reaction. Let's take a look at the second one. Now, in the second one, there's a couple of steps. So in the first step, I have an alkene and water in the presence of some acid. So what can possibly happen is I can have an addition reaction because it's a double bond. That's all it can do. The addition reaction produces an alcohol, right? Because H goes to one side, HOH, or the OH goes to the other side. That now is reacting with methanol, and it's creating this particular molecule. So let's investigate. So this is your ethanol, and I'm going to horizontally flip this methanol so it looks this way. So if I were to remove the water, then I get back an ether plus some water. So if I look at this, I've got 1, 2, here's my methyl, and here's my ether with the, sorry, ethyl, and this is my methyl. So first step is an addition reaction. Second step is a condensation reaction, correct? Naming ethene, water, ethanol, methanol, and then this would be called methoxyethane. Let's take a look at C. Now I've got a carboxylic acid with a benzene, so benzoic acid. Okay, and then I've got 1, 2, 3, and then I've got propanamine. This comes together somehow and links up with the amine. Well, what could be happening is if I isolate the 2 hydrogens, then I could be condensing it, right? And the nitrogen hooks up to the carbon, makes sense, and then the 3 carbons thereafter. So this is a condensation reaction. Okay. Number 2, write the formula for the primary amine produced from the reaction of iodocyclopentane. So first, let's draw cyclopentane. It's my house. Put the iodine there. And we're going to react it with ammonia. Okay. This is often in the presence of sodium hydroxide that helps this reaction as well. And so we get a substitution reaction where the NH2 goes here, and then you end up making sodium iodide and water. Okay. All right, complete the following equations by writing the structures that form or the reactants required. So when I look at this one, bromocyclohexane and ammonia is the same thing as number 2. Ethanol and propanol, well, let's draw it. Ethanol combines with propanol. There's propanol. What's going to happen? We're going to lose water, right? And we're going to end up making an ether just like we did before. Over here, I've got an ether and I'm adding water. So really, it's the opposite of this reaction where the hydrogen hydroxide will go, the hydrogen will go to the oxygen, right? And the hydroxide will go to this side. And I'll regenerate my alcohol, 2 alcohols, right? So what would have come together to make an ester bond? Well, an ester bond is made by an alcohol and carboxylic acid. So I'm going to break it off right here, right? And what's going to happen is the water, the hydroxide will go on this side, the hydrogen will go with the oxygen. So technically what I had started out with was a benzene with a CH2OH plus propanoic acid. Okay, and if you guys take a look at the rest of them, they're all basically repeats of condensation reactions. Completely doable, but again, if you have any questions, we can take them up tomorrow. So yesterday, I uploaded more practice problems, and one of them is on synthesis reactions. Okay, so synthesis reactions is the culmination of this unit. If you can do synthesis reaction, it means that you have a thorough grasp of the unit. And you can conceptualize what each one makes and how and with what. And you can bring it all together. So take a look at propane to propanone. And those are the type of questions that I would likely be putting on a test, is synthesis reactions, because it brings everything together. It's at the higher level thinking. So if I have propane, 1, 2, 3, and I need to make propanone. I know that from what I taught you, you cannot go straight from a hydrocarbon to a ketone. No way. No way, no way. I told you that carbon-hydrogen bonds are very stable, and because they're stable, they don't just start reacting. You have to introduce some sort of functionality so that they can start reacting. So the way that I go about looking at synthesis reaction is I do a backward thought process. It's based on the functional group specifically. So my focal point is the fact that I have a ketone and it's right here. So I think to myself, how can I make a ketone? Well, ketones can be made when they're subjected to oxidation with potassium dichromate. And it's always potassium dichromate plus an alcohol. Well, if my oxidation reaction makes a ketone, it tells me that I need a secondary alcohol. So I can't put the alcohol on the end. It has to be here. The other way of thinking about it is if this became double bonded, this was an OH before, right? So I know that in order to make a ketone, I require some sort of an alcohol, specifically a secondary alcohol. So that's my backward step here. Now, when I look at this, my propane, and I look at my 2-propanol, there is still no direct way of going from here to here. Okay, so the question is, how or where could this alcohol have come from? So if we go back in our notes, we know that there are two ways of making alcohols. I'll bring up your class note and we'll go up ever so slowly, ever so slowly. And I want you to look at hydration reactions and double bonds. And of course, it won't let me. It won't let me. So one way of making an alcohol is through taking a haloalkane and reacting with sodium hydroxide to substitute it. The second way is taking an alkene and adding water to it. So really, I have two ways of getting to the alcohol part, and I'll show you both ways, don't worry. Okay, so one way is to substitute. So if I had my, let's say, chloropropane, I can react that with sodium hydroxide, and the hydroxide will substitute here and make the alcohol. Okay, but how did I go from here to there? Well, if you guys think about it, if I take UV light, right, and I react this with chlorine, I'm going to have free radical substitution where it will go on all different carbons, but I can isolate for this one, can't I? Right? And so now I can take this route and I can make the alcohol by substitution and then oxidize it. So there's 1, 2, 3 steps. Now, what if I took a different route? What if I made this by starting with propene? Okay, starting with propene, when I react it with water, right? Markovnikov says hydrogen will go here, hydroxide will go there, which is what I want. Okay, and so I can go this route to make the alcohol, but can I go from here to there? The answer is yes. What if I use cracking? What if I heat the bejeepers out of it and add that double bond and then hydrate it and go this route? Okay, there's yet another way. I know, so crazy. Another way is, what if I start by catalytic cracking? Okay, so I heat it, I make my propene, Okay. And for some reason, I decide I'm going to react this with the HBr. Okay, still doing addition reaction. And I end up getting this because it's still Markovnikov directed in the middle. Now I can take this and I can still react it with sodium hydroxide, and I'll get here in that route as well. So there's a couple of ways, 3 routes really, in which you can get to the end product. But notice how I went about it. Backward design, that's what it is. Sometimes it's obvious, sometimes it's not. And when it's not, you're going to focus on the end product and jump backwards stepwise, 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 until you reach a point where you can regenerate the original reactant. Any questions, you guys? Any questions, por favor? I don't know what's wrong with me today. French and Spanish. Okay, so let's take a look at the second one. Let's take a look at the second one. I said, let's take a look at the second one, and it's not scrolling. We will force. Starting with the appropriate alcohol, make 1 pentene. So I want you to ponder that, and I'm going to do attendance. Syed, are you here?
Here.
Achala? Achala, are you here?
Yeah, I'm here.
Okay. Hi, Dara?
Here.
Katarina?
Here.
Puneet?
Here.
Mona?
Here.
Ayushi?
Here.
Noel? Noel? Kartik? No Kartik? Nilasha?
Here.
Krish?
Here.
Dante?
Here.
Disha?
Here.
Rusha?
Here.
Ishmael?
Here.
Mahi?
Here.
Nishan?
Here.
Hamisha? No Hamisha? Ria?
Here.
And Nadia.
Here.
Okay, so let's take a look at,
Miss Hamid,
yes?
Noel just texted me that his internet crashed. He'll be back in a moment.
Okay, thanks for letting me know. I'll take him off the absence. Okay, so starting with the appropriate alcohol, make 1 pentene. So we're trying to get to 1 pentene. So I always draw out the product, 1, 2, 3, 4, 5. So it says starting with the appropriate alcohol. Is there a way for me to go from alcohol straight to an alkene, you guys? Yes or no? Is there a way? So what am I doing here? What kind of reaction is this? Oh, and it's going to disappear. It's an elimination reaction technically, right? Am I able to eliminate an alcohol group? So am I able to dehydrate? Sorry.
Yeah, could you do it by adding like concentrated, I think sulfuric acid?
Love it. Yeah, so we're going to add sulfuric acid, and that will get us directly to the alkene, and it will make water. Now, we want 1 pentene. I just want to give you some other things to be aware of. 1, 2, 3, 4, 5, 6. Now, notice how I did 1 pentanol to make 1 pentene. And the reason why I did 1 pentanol is, like, I could have put the OH here, correct? And I can still remove hydrogens from here. The deal with chemistry and nature is that when it makes a double bond, it wants it to be more substituted. So it prefers to take this off. Some will happen here, but not mostly. So it will actually, if you put the alcohol in the second carbon, you will most likely get 2-pentene as a higher yield than 1. Because when I do 2-pentene, then I've got a CH3 on this end, and then I've got 2 CH3, and then I've got an alkyl group on the other end, and hydrogen, hydrogen. Here, I only have one alkyl group. So the idea of having these alkyl groups support the double bond forces this sequence as opposed to the other ones. So the only thing you need to do is just be aware of these little nuances. If you were to do 2-pentene, or if you were to do 2-pentanol and you went this route, I would close my eyes and pretend, okay, they're taking the minor product and doing it. The ideal way is to focus on the sort of Markovnikov directed products or things that, impact the outcome. And this you wouldn't know of, right? I told you this now, but you wouldn't know of that without me telling you this. And you could anticipate that this would make 1-pentene. So I wouldn't hold it against you, but I'm just letting you know that if you come across certain outcomes on the internet, it's because they're thinking about the stability of the product more so at a higher level. Okay, so I'm done. Your job is to continue struggling with these. I'm going to upload notes for introduction to mechanisms. So we're going to do a bit more synthesis problems tomorrow. And then I'm rolling right into mechanisms. I'm going to upload the note today. And we're going to get started as soon as possible because the longer it kind of stays in your brain, the better chance of it kind of settling. So if I introduce it by Friday, or even tomorrow, and then roll into it on Friday, then you have the weekend to kind of sleep on it, like literally. And then Monday I'll go over it again, and then we'll take off from there. All right. Any questions before I let you guys roll out?
Ms. Ahmed,
Yeah.
can you post yesterday's lesson on Google Classroom as well? I just wanted to go over it again, just to get it.
Sure. Yeah. I thought I did. I must have forgotten. Yeah, I can do that.
Thank you.
That's it. All right. Have a good day, everybody.